Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Soyola Alua, and I'll be walking you through the physics course. We'll be considering simple harmonic motion. And in this topic, we'll look at the definition of simple harmonic motion. We'll consider some illustrations of simple harmonic motion. We'll look at the relationship between simple harmonic motion and circular motion. We'll look at acceleration in simple harmonic motion. Then we'll consider period, frequency, and the amplitude of simple harmonic motion. After which we'll consider energy of the simple harmonic motion, and then damped oscillations, and finally forced vibration and resonance. What is simple harmonic motion? Well, just like the name sounds, it is simple, it is a motion, and it is harmonic. In other words, it's a motion that is systematic and it is constant. It follows a kind of a tune, just like a music. When the body is having a vibratory motion, or it is moving to and fro, like in the music, that's why we put that word harmonic. It's kind of like synchronizes. It moves consistent. It is consistent. We say it possesses the simple harmonic motion. Well, the reason why it is more simple, why we use the word simple anyway, is because we are considering that external forces are not being involved. So a simple harmonic motion has an acceleration which is towards a particular point. It is towards a particular point. The acceleration, when it gets to a certain point, it develops no speed, zero velocity, and then it accelerates again and then decelerates at the middle and then gets to zero velocity and comes back again, and it has one maximum acceleration which is heading for one particular spot. Let's take some illustrations of simple harmonic motion. Where you take something, maybe a stone, and you tie it to a thread, like I have a charger here, and you hold it up and you displace the weight to one side, then let go. It kind of swings, and then it's stopping. Well, the reason why it's stopping is because there is what is called air resistance. So it is doing a work against air, and the air is actually pulling to a stop. But let's assume that I happen to be in a particular room where there is no breeze, where the air is still. It will keep swinging. Those of us who have houses where we have pendulum clocks, you would have a very good knowledge of this. You would be able to explain it better, because you just see a pendulum clock, it always moves. The pendulum bob will always move. And another illustration again of simple harmonic motion we see is in our spring, your conventional spring. You can take your spring and you pull it, and then it will vibrate, something like that. It is exhibiting simple harmonic motion. Another illustration can be a test tube. Take a test tube and fill it, not to the brim of course, but fill it to a reasonable point where it has enough weight, and you place it on water. It would want to sink and then to come up and then go down, and after a while it will kind of like find its balance. Illustrations of simple harmonic motion come to play, but only that in real life situations there are other barriers which make this harmonic motion no longer that simple. In a few seconds, some questions would show on your screen to test your knowledge of what you've understood of what has been taught so far on simple harmonic motion. Please attempt them. So, let's see the relationship between simple harmonic motion and circular motion. Of course, if we look at the conventional simple harmonic motion, that is the one involving the pendulum bob, you'll see it is something like it's moving to and fro, and you see something like a kind of a sector being created, something that looks like this. So we can easily relate simple harmonic motion to circular motion, and there are certain parameters that we must always consider. Of course, those are the parameters that help us to understand circular motion. One of such parameters is what we call the angular velocity. I made mention of it to us earlier in one of our earlier topics, but we didn't really look into it as that. So today we'll be considering angular velocity, and we'll be trying to understand what the concept of angular velocity is all about. We're bringing our simple harmonic motion into a circle. Now let's imagine it being a complete circle. Of course, since it will not complete the full circle, we will only cover a particular angle. So let's take that angle to be theta, and this is the speed at which it is moving. That's what we call angular velocity, mu. Angular velocity, mu. It's pronounced as mu. Some people do call it omega, but it's mu. So mu, and we have mu is calculated as theta over time. It is calculated as theta over time. Angular velocity is the degrees covered in a certain time. The degrees covered per unit time. That is the amount of degrees covered in a second by the object. So since we are moving in a circle, then it is possible to measure the degree. So we'll take our angular velocity to be theta over time, and it is measured in radians per seconds. It is measured in radians per seconds. Okay. So how do we now calculate our theta in radians? Because I know many of us do not really know how to go about the calculation of that in radians. So to calculate our distance in radians, all we just need to do is we take a measurement of what this place is, that is that curved part. We measure it and we label it as S, and we also take a measurement of the radius. So the angle is facing the curved part, so we say our theta, theta equals S divided by R, that is the radius. So we can take our S to be equal to R theta. So if we want to take our S to be actually, the S is actually our distance covered. Is the distance covered within that period. So the velocity, or rather what we would actually have is not velocity but speed, because we are not moving in a straight line. Our S then equals to R multiplied by theta. So I was explaining to us earlier, when we talked about vectors and scalars, we said velocity is a vector quantity, which means it exists only on straight lines. And I told us that day that there is actually a condition where velocity may not be on a straight line, and it was called angular velocity, and that is what we have here. So the speed with which the body is moving can also be calculated as the distance covered by the body, that is the pendulum bob or the dead weight we're talking about, or whatever object is moving within the to and fro motion. The distance covered in that to and fro motion divided by the time it takes to cover that distance. And the distance covered is S. So we can say our speed or velocity equals S divided by T. And we have also said that our S is R theta. So we can say velocity is also going to be equal to R theta divided by T. And if we look up here, we are saying theta over T equals to angular velocity. Thus, we can say our velocity, the velocity with which it would move, would be equal to r multiplied by angular velocity. So the radius, that is which would actually mean the length of the twine or the rope that is used to hold the dead weight, the radius multiplied by the angular velocity, that's the speed with which it is moving in the angular film, is equal to our actual velocity. That is relating, that's the relationship between, that's one of the relationships rather between simple harmonic motion and circular motion as regards velocity. Well, we always define acceleration as the rate of change, the time rate of change of velocity. Acceleration is the time rate of change of velocity. In like manner, angular acceleration is also the time rate of change of angular velocity. Angular acceleration is the time rate of change of angular velocity. So, angular acceleration is represented with alpha. It is represented with alpha. And of course, from what we were taught earlier, in the last thing we considered, the other time we talked about angular velocity, and we said it is mu. So, rate of change, that is to be equal to, if there were two velocities over time. That's if there were two different velocities. So, we want to establish the relationship that exists between angular acceleration and actual acceleration. Angular acceleration and actual acceleration. Let's recall that in the last proving, we proved that v equals to r mu, that is, the actual velocity equal to radius multiplied by the angular velocity. And of course, since rate of change of time, this is what should be. So if we should substitute, our mu into the equation, let's first make mu our subject formula from here. That will give us mu equals to v divided by r. Now putting this into what we have up there, we would have our alpha to be equal to v2 over r. Now take note of this. We are talking about the same system. That is, it is the same pendulum bob, it's the same rope. It is only changing velocity. So r would be the same for both of them. There will be no change in r. The same twine is in question. So v2 over r minus v1 over r, everything divided by t. To make things easier, we can bring out our r and put it outside. So we have alpha equals 1 over r into bracket v2 minus v1 over t. So, to continue solving, well, if we look at the expression, the other time I defined acceleration. I said acceleration is the time rate of change of velocity with time. And if we look at what we have on the board here, this is velocity minus velocity, and this is time at the bottom. So this alone on its own, as it is here, is acceleration already. So our angular acceleration can then be said to be equal to our conventional acceleration divided by radius. So we can say our acceleration equals to alpha r. That is, a equals to alpha r. So the expression stands that our angular acceleration equals to the actual acceleration divided by the radius. So actual acceleration would also be equal to angular acceleration multiplied by our radius. Let's also keep in mind velocity is also equal to radius multiplied by angular velocity, or angular velocity multiplied by radius, whichever way you choose to arrange them. Period. The period is the time it takes a body to perform a complete revolution or an oscillation. It may not necessarily be moving the complete circle in a pendulum, moving that from the toe point to the fro. That's the complete revolution. Now, the period, by practicals, we can calculate our period with the formula T. The period is represented by T. It can be calculated with T equals to 2 pi the square root of L over G. This is via experiment. Via experiment. Or if you're given parameters, maybe you're told a pendulum ball was attached to a string 50 meters long, then you can go ahead and use the formula. And also, next thing we have up there is frequency. Next thing we have up there is frequency. The frequency is the number of complete oscillations that is made in a unit time. The number of oscillations that is completed within a unit of time. That unit of time usually is seconds. Of course, your period can be in minutes, can be in hour, can be in second, since this time. But standardly, our period is usually measured in seconds. And frequency goes, it's calculated as the inverse of period. Since the period is the time taken to complete an oscillation, then when you calculate its reciprocal, you get how many oscillations can be made in a particular time. Frequency is measured in hertz, and hertz is actually the same thing as 1/second. So many times, many of us have had, I want to buy, you say you want to buy an electric bulb, you say you want to buy an electric bulb, and maybe some of our home appliances and other things, you see on some of them labeled 50 hertz, 60 hertz. Well, this is what they're talking about. Frequency, the frequency at which the particular appliance operates. And also, we have amplitude. Amplitude is the height of the wave, or the length. Let's go with the word height. Is the height of the wave. It is the maximum height reached by a wave. It can be calculated in different ways and depends on what waveform we have.
Action.
Energy in simple harmonic motion. We have come across a particular question before about simple harmonic motion, where we talked about energy. And I remember at that day, in that particular video, we said something about maximum PE and maximum KE. Yes, we're talking about law of conservation of energy. The same thing applies. It still holds. It hasn't changed. Because energy in the system does not just vanish. It is going to be used up, as in it would either be converted from one form to another, or it will just remain there. So in the simple harmonic motion, at this place, which is the maximum height that the bulb swings to, we have PE and KE. The PE is at maximum, while the KE equals 0. Why? Because when it gets to that particular spot, the body will stop moving. And we all know that PE is calculated, KE is calculated, that's kinetic energy, is calculated as half mv squared. So, since it is not moving, that means there will be no there will be since it's not moving, that means there is no velocity, and hence no kinetic energy would be possessed. So the same thing applies at this other end. PE is at maximum while KE equals 0. Now at this center point, KE is at maximum while PE equals 0. This center point represents the baseline of the entire system of the simple harmonic motion. At this center point, the height of operation of the simple harmonic motion equals 0. This is the baseline, this is the origin point. So it's like, of course, we know our PE is calculated by mgh. Now the h is measured as the distance between when it is vertically down and every other height. So at vertically down and vertically down, the whatever thing you want to measure would be 0. So since h is 0 at this particular point, then potential energy in it would be 0. So the h is air. Now all these energy, that is the kinetic energy or the potential energy, it's still dependent on the initiating energy. Now in a spring, you have to relate it to the spring energy, which is the spring energy is calculated by half Ke squared. So if it is in a spring system, you also will work with half Ke squared. In other systems, depending on what the source of energy is. Yes, it's also important to note the total energy of the system remains the same throughout, always, except an external force or an external device is taking part of the energy. So in simple harmonic motion, we ignore friction and we ignore air resistance. So it is taken that the total energy of the system at every point in time is constant, even though which means that the causing effects, that is whatever thing is causing the energy, whatever source of energy, whatever source the energy is being gotten from, that source, the amount of energy provided by that source would always be equal to Ke plus Pe. So if the energy is coming from the spring, it will mean Se will be equal to Ke plus Pe. If the energy is coming from a push, maybe a force, that is force times distance, it will be equal to Ke plus Pe. Let us bear that in mind. If it is coming from a particular work, it will be equal to Ke plus Pe. Damped oscillations. When we talk about damped oscillations, it means the kind of oscillations that we have been looking at with our two eyes. All this while I've been talking about simple oscillations, simple harmonic motion. Well, if you remember the other time I was holding something, I told you in an ideal situation, the velocity and the acceleration should be uniform. It would always get to the point it started from. But of course, you observed that it was not like that. That's what happens in damped oscillations. In damped oscillation, the oscillation starts large. The amplitude is high, is very high if it's very large. And as time goes on, it reduces and reduces and eventually comes to 0. This is because of friction, air resistance, and other dampers. you can actually introduce a damper into the system. Well, damped oscillations, the knowledge of damping actually helps us in reducing noise pollution and in development of certain kind of systems. Like the exhaust system of your car. First, vibrations and resonance. Let's talk about vibrations. Vibrations, of course, we already know what those are. Alterations, that is, movements. Basically, you see a wave in work, a disturbance in nature. So, we'll talk about resonance. Resonance is the transfer of vibration from one body to another body, because it's transfer of energy from one body to another body, vibrational energy or vibratory energy from one body to another body, and both of them being at the same or very, very close frequencies. That is it's the knowledge of this that we use to receive radio waves, radio signals in our houses, on our television sets, on our mobile phones. The frequency at which the television station broadcasts their television programs, you tune your television sets to that same frequency and you're able to watch what they have to show you. So we see the application of simple harmonic motion and waves at work in our day-to-day lives. A 10 kilogram mass is suspended from the end of a spring and released. If the spring oscillates in simple harmonic motion with a period of 0.5 seconds, find the energy given to the mass if the amplitude of oscillation is 2 centimeters. Okay, let's write out our parameters. The first thing we know is the mass of the mass that was suspended, which we know to be m, equals 10 kilograms. Also, we know the period, that's t, and t is 0.5 seconds. Well, we're asked to find energy, and we know the amplitude. Let's call that A, equals, let me put that here. Amplitude equals 2 centimeters, and converting 2 centimeters to meters, we have 0.02 meters. Okay, let's start work. I know you don't have this formula, but when it comes to period for springs, you can calculate period for spring as T equals 2 pi square root of mass divided by spring constant. 2 pi square root of mass divided by spring constant. So, using this formula, we can introduce our parameters into the equation. We know our period to be 0.5. We know, of course, 2 pi is 2 pi, and then the square root of, we know m is 10 and k we do not know. Well, I would like to take this other side, and I want to try to make k the subject of formula. So for now, I'll bring this down here. That will give me 0.5 divided by 2 pi equals square root of 10 over k. Squaring both sides. So I'm squaring both sides. If I square this, that will give me 0.25. Squaring this will give me 4, and I'll have pi squared equals, when I square the whole expression, I'll have 10 over k, because the square root will be taken off. So I want my k to be up. I want all these other things on this other side. So my k equals 10 multiplied by 4 pi squared divided by 0.25. Well, dividing this way, it simply tells me I'm going to multiply 4 to whatever I have up there. So my k, if you press it on your calculator, you have something like so our k is calculated as 160 pi squared, and the unit is Newton per meter. That's our spring constant. Let's keep this answer up here because we need it to calculate the energy. It has to do with the energy. There are certain things we need to keep in mind. The amplitude at which with which our body is vibrating, that is the extension that is experienced in the spring. So that amplitude, it is called amplitude. Yes, it is an amplitude. It could also be described as the extension of the spring. So of course we know that, so we can actually put also is E, small e. And our spring formula, our spring equations says energy, that is spring energy, equals half ke squared. Half ke squared. So using our k, which we've gotten, multiplied by 160 pi squared multiplied by that's 0.02 squared. When we enter this information into our calculator, the results would be 0.032 pi square joules. So that's our answer. We're asked to find the amount of energy the body that is given to the mass. So that is the amount of energy that will be given to the mass. In this topic on simple harmonic motion, we looked at the definition of simple harmonic motion, where we say simple harmonic motion is a motion which is between two fixed points, using a uniform acceleration between two fixed points. We looked at some illustrations. We considered the illustration of a simple pendulum. We considered that of a spring. We also talked about a bouncing tennis ball, and as well a test tube. We talked about the relationship between simple harmonic motion and circular motion, where we defined and we talked about we looked into velocity and angular velocity, and we found out that angular velocity equals to velocity divided by the radius. We also looked at the acceleration of simple harmonic motion, where we discovered that acceleration, that is angular acceleration, also equals to acceleration divided by the radius. We defined period as the time taken for a body to complete an oscillation, and frequency is the number of complete oscillation made within a duration of time, a unit of time. And we talked about amplitude as the maximum height of displacement the body makes in the course of the motion. We looked at the formula for calculating we looked at the energies involved in simple harmonic motion. Those are the potential energy and the kinetic energy. And we also talked about other energy forms, which is in cases of springs, we'll come up with spring energy, which might be involved. We talked about damped oscillations, that oscillations might be damped, that is, can slow it down, introducing friction. And in resonance, we talked about resonance, and we said in resonance, when a body is in a place and another body is in another location and they are at the same frequency, energy can be transmitted from one body to the other. That is, from the body A, energy is being transmitted to body B at the same frequency. I explained that was how we receive our television programs from the television transmission stations. So some questions will pop up on your screen in a few seconds. Please attempt them. And if there is anyone you find a bit challenging, you can watch this video one more time. Thank you.